moving ahead in the lecture, the next piece is the complement of an event. Okay, so this is going to be a big idea as we move deeper into statistics later in the course. Probably the one concept that I really want you guys to take away from this chapter, and everything is important. Everything is important. But if I could highlight the most important concept, it's the complement. So what is the complement of event A? It's all outcomes for which A does not occur. And it's denoted by A with a bar. Now, we wouldn't read that the same way as we did X bar in the previous chapter. Here, when you see the A with the bar over it, we read that as A complement. So you see this, and we think, okay, that's A complement. Has a similar notation to the the sample mean, the X bar, but a very different concept for us here in probability. A complement. Again, it's the outcomes for which A does not occur. So think of it as the opposite of event A. And I've got a formula there just below. Let's skip that and just jump right into the practice problem, and then we'll come back and make sense of that formula just above. Practice number 3. In a family of 3 children, let's say event A is to have exactly 2 girls. All right. Part A, what outcomes are in A complement? All right, so what we're setting up here, and what you see there on the screen on my page. So we're saying event A is to have exactly 2 girls, and we kind of done this a couple times. So I just went ahead and listed the ways a family of 3 could have exactly 2 girls, right? So we had the oldest is a boy, and then the 2 girls. The middle child is a boy, girl here, girl there, and then where the youngest child is a boy, so oldest, middle are girls. So that's event A. Now there is a sample space that has all the possibilities for the kids, but we're focusing here. Okay. Part A says, what outcomes are in A complement? All right. So A complement is going to be everything else. Actually, let me go back and grab. It would be good maybe to have all this on the screen. You probably got it written down. If I can fit all of this, that would be helpful. Okay, so this was our sample space from before. Oh, I'm like showing you. Okay, so that's event A. A complement are all of the other events. Okay, so event A back here, like this was event A, right? There are exactly 2 girls. Those three. So then A complement is everything else. We just take all of the other possibilities. So boy, 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 girl, boy, girl, boy, girl, boy, boy, and girl, girl, girl make up A complement. All of the ones that are not in A fall in A complement. It's the opposite of A, if you will. Okay. That was good. So what is part B? What is the probability of A complement? Well, of course, we could do probabilities of a complement just as we can do probabilities of A. So we'll think, okay, the probability of A complement here, well, there are 5 parts to A complement. There are 5 ways. So we say 5 divided by, and the total is still 8 because we're thinking the total is from the sample space. So 5 out of 8 gives us 0.625, and we got the fraction and the decimal versions there. Okay. Now I think we can go and make sense of that formula. So it said the probability of A equals 1 minus the probability of A complement. And so I've repeated that formula here. Would that be true of this example with the 3 kids in the family. And, if event A is having 2 girls. And, well, yeah, it would. So if we think, hey, the probability of event A, well, that was 3 out of 8, right? And the probability of A complement we just found was 5 out of 8. Is this really true? Is 3 over 8 equal to 1 minus 5/8? And yeah, it is. And depending on how comfortable you are with fractions, we can think of 1 as 8 out of 8. And yep, this would work. 8 over 8 minus 5 out of 8 would be 8 minus 5, which is 3 out of 8. So it holds. And this formula is really the power of the complement. So it turns out, we'll see this in the next 2 examples, 4 and 5, practice problems, I mean. We'll see this in action. The idea is, oftentimes, we want to know the probability of A. But because of the circumstances and the way A is defined, it's very difficult to find the probability of A. So what you do is you find A complement and then the probability of A complement, which turns out to be a lot easier. And then you do 1 minus the probability of A complement, and that tells you what you're after, the probability of A. Okay, maybe that makes sense, maybe not. Let's go ahead and do practice 4 and see it. Okay, so there's my first line. Let me read it, obviously. Practice number 4. In a deck of 52 cards, 4 cards are drawn. After each draw, the card is placed back into the deck, and they are shuffled before drawing again. Okay, so we got this deck of 52. We're going to draw 1 card, look at it, and then we're going to hand it back to whoever is holding the deck. They're going to reshuffle it, and then we draw again until we've drawn 4 cards. So each time we put the card back, that's important. That's another concept going to come up pretty soon, that we are always putting the card back in the deck. So every time we draw, every card is possible. Okay, what is the probability that at least 1 ace is drawn out of all your 4 draws? What are the chances that you get at least 1 ace? And you might get more than 1 ace, that'd be fine, but at least one of those is an ace. So we're going to say event A here, at least 1 ace. All right. So it turns out to find the probability of A directly is not easy. That would be a lot of work. Okay. So I've kind of noted that here. Finding the probability of A is difficult. It's certainly not impossible. But why would it be difficult, you might ask? What's the big deal? We've been doing stuff like this already. And the difficulty lies in these words, at least 1 ace. Let me kind of break it down for you why this would be difficult. At least 1 ace means there could be exactly 1 ace, or there could be exactly 2 aces, or there could be exactly 3 aces, or there could be exactly 4 aces. And remember, the order matters. So let's say, you wanted to find the probability of getting exactly 1 ace. Okay, so you have to say, well, maybe it's the first card that's an ace, but then the second is not, and the third is not, and the fourth is not. So you'd have to find those probabilities and multiply them. We can think, well, wait a second, maybe it's the second card that's an ace. So the first is not, but then the second one is, and then the third is not, and the fourth is not. Okay, and then we have to think, okay, what's the chances that the third one was an ace? And you kind of get the idea. You're like, well, yeah, that's some work there to find all the ways that you can get exactly 1 ace. But that, that doesn't really seem all that bad either. Okay, but that's just getting exactly 1 ace. Then you have to think about getting exactly 2 aces. And the different ways that can happen are going to go up. So maybe it's the first and the second card that are aces, and the second and the third are not. Or maybe it's the first card that's an ace, the second one is not, the third one is, the fourth is not, right? And we're multiplying these all together, right? Okay, so we'd have to go through all the possible ways we could get exactly 2 aces. Then it's time for 3 aces. What are all the possible ways of getting 3 aces, right? And we're kind of adding each of these up as we go. And then finally, all the possible ways of getting 4 aces. Well, there's actually only, that's a little bit easier than some of the others because they're all aces. But anyway, it's no short amount of work. It would take you, probably a good page of work minimum. And you got to keep track of all this, and that is sometimes problematic as well, just keeping track of your, okay, anyway, so maybe I've made my point. Finding the probability of at least 1 ace is tough, and it's really that phrase at least that gets us. So instead, we're going to make our work a lot faster if we think about a complement, okay? Instead, we're going to find the probability of a complement and use our formula. Okay. So, if A is at least 1 ace, how could we describe a complement? What's the opposite of at least 1? And, well, this would be a lot more interesting if we were all in class together and people could respond. And I found that in a classroom full of students, at least a couple people know fairly soon. Sometimes it takes a minute or two to kind of wrestle with it. What is the opposite of at least 1? But it's not unusual for a couple of people in the room to know what the opposite of at least 1 is. And, well, it's none. A complement here would be no aces. At least 1 means 1 could be an ace, 1 of them, 2 of them, 3 of them, or 4 of them. And the only option other than that is that there were 0 aces. So the opposite of at least 1 is none. A complement means no aces came out. Okay, so this is really simplifies our work. All we got to do is find the probability of getting no aces, and then we'll do this 1 minus formula. Okay. Let's find the probability of getting no aces. And I'm gonna write all this out, make sure you follow along. There are 4 components. So we need to look at them one at a time. The probability of a complement means we don't get an ace on our first draw, right? The probability of no ace on the first draw. Then we're going to put that card back. They're going to shuffle it. We're going to draw again. And, well, we're not going to get an ace on the second draw. Same thing a third time. Shuffle it, put the card back. Shuffle it, draw again. We don't get an ace on the third, and we don't get an ace on the fourth. And again, we multiply these 4 probabilities together. Okay, now let's talk about each one of them. Turns out they're all going to be the same here. Here we go. Probability of a complement. Okay, so let's look at this first one. The probability that we do not get an ace on the first draw. So there are 52 cards, right? So divide by 52. And for the number on top, we just have to think, okay, how many cards in that deck are not an ace? There's 48 non-aces, right? There's 4 aces, so 48 of them are not an ace. Okay, 48 out of 52 chance that we don't get an ace. And, once we draw that, all we do is look at it, we put it back in the deck. So the chances of not getting an ace on that second draw, still 48 out of 52. The third, still 48 out of 52. The fourth, still 48 out of 52. And we can multiply all of these together. Now maybe you notice something. Hey, since they're all the same number, we could use an exponent here. This is kind of, what's your personal preference? 48 out of 52 to the fourth. And so you can just grab your calculator and type that in. And here, we just want the decimal for the time being. So this was the decimal rounded to 3 places, 0.726. But wait, we're not done. That is the probability that none were aces. So now we got to go, here's where the formula comes in. I'll just show you all of my work from here. The probability of A, which is what we're after, is 1 minus that. 1 minus 0.726 is 0.274. And there's our answer right there. This was the probability of no aces. So this is the probability of at least one ace. And much, much, much easier done this way. Not that it was immediate. There was still definitely some work and some thinking, but nowhere near as long as what it would have been had we tried to do it directly. Okay. The power of the complement. Let's move on to number 5. It's a similar situation, but now we are tossing a coin. We haven't had an example where we're tossing a coin. So these come up, you can imagine, fairly regular when it comes to probability questions. Okay, let me go ahead and read it. It says, practice 5, a coin is tossed 5 times. Find the probability of getting at least one tail. All right, so you've got your coin. You're going to flip the coin, take a look at it, flip it again, take a look, right, 5 times. What's the probability of getting at least one tail? And you think, well, probably pretty good, right? You're tossing a coin 5 times. The chances of at least one being a tail, quite high. Well, that's true. Let's see if we can calculate it. So I'm going to describe event A as being at least one tail. And again, we see that phrase at least. Okay, big tip here. When you see the phrase at least, that is a huge hint that you'll use the complement. Okay, see the phrase at least, find the opposite of that, find the probability of that opposite, that complement, and then do that 1 minus, and that's going to be the approach. Okay, so kind of similar to the previous problem, what is the opposite of at least one tail? And again, it's none. So you might describe a complement as no tails. We never flip a tail. Now, because there's only 2 possibilities for each coin flip, saying no tails is equivalent to saying they all come out as heads. And that might be easier to just think of it that way. Every time you flip this coin, you get a head. Okay. So let's find the probability of a complement. Here we go. We're flipping the coin 5 times. So this is the first flip of the coin. And we need to get a head. Right, head on the first flip. Then we pick it up, we flip it again. We need to get a head on the second flip. Okay, and so on, the third flip, the fourth, the fifth. There's always a 1 out of 2 chance, right? There's 1 head out of 2 possibilities for getting a head on each one of those flips, and they all get multiplied. And so you might think, hey, I'm multiplying the same number 5 times. So that's, sorry, my little, not quite as dark, this writing for some reason. So that's 1/2 to the 5th. You could also think of 1/2 as 0.5. That'd be fine too. Let's calculate that number. If you think of it as 1/2 to the 5th, that's 1/32, or maybe you just go immediately to the decimal. That's really what we want here. The probability is 0.031. So the chances of flipping 5 heads on 5 flips of the coin is quite small, 0.031, just a tiniest bit above 3%. And you might expect that all of them come out as a head. Okay, but of course we're not done. We need to do the 1 minus. So the probability of at least one tail 1 minus 0.031 turns out to be 0.969 when we go to 3 decimal places. Very high, almost 97% chance of getting at least one tail. And that fits probably with our understanding of flipping coins. You flip it 5 times, that tail is very, very likely. You know what, though? That previous problem, that answer was kind of surprising. Okay, so we're done with this one. I didn't mention this earlier, but I think I'll go back. Right, at least one ace. Right, you're drawing 4 cards. The chances of at least one of them being an ace is over 27%, 0.274. More than a quarter of the time, you're going to get at least one ace. And that seems very high. I would think the chances of getting at least one ace are, quite a bit lower than that. Maybe even like half of that or less. But no, over a quarter of the time, over 27%, that you're going to get at least one ace out of 4 draws. So sometimes these things, they surprise you once in a while, these probabilities. Okay, just kind of my reflections. Let's stop this video here, and we will pick it up with the next.